Okay, hey, welcome back. This is basically the last test that we have to learn, the ratio and the root tests. We'll use the ratio test the most, so the root test is there, but it's not used as much. So anyways, here we go. So first, kind of just defining what these tests are. So first, the ratio root test. So we're going to take a series and the terms are just, they have to be non-zero, but you can have plus, minus, and negative, plus and minus terms in there mixed in. So let the series a sub n be a series with non-zero terms, and then consider one of two objects. So for the ratio test, you consider this number r, which will be the limit of the absolute value of a sub n plus 1 all over a sub n. This is the ratio test. Or for the root test, you consider r, which will equal the limit of the nth root of the absolute value of a sub n. So that's the root test. And then based on the r value, you can make a conclusion about the convergence or divergence of the original series. So first, if the r value is less than 1, the series is absolutely convergent. Okay. Secondly, if the r is greater than 1, or r is equal to infinity, then the series is divergent. Then thirdly, if r is equal to 1, the test is inconclusive. Okay. So you have to try something else. Let's go ahead and take a look at maybe some examples, and then we'll hit the proof. So let's look at, I want to see how far I need to, if I can give you this as the video quiz. Sure, let's make this the video quiz problem. Let me mark this in my notes. So this is 9.6, and the video quiz is the Sky series 2 factorial. Okay. So our example is the series 2 to the n over n factorial going n equals 0 to infinity. Okay, and we're going to do the ratio test on it. So I do the limit of the absolute value as n goes to infinity, limit of the absolute value of a sub n plus 1, which is 2 to the n plus 1 all over n plus 1 factorial. And then divided by a sub n, let's just multiply by the reciprocal though. Okay, so times n factorial all over 2 to the n. Okay. We can use just general properties of commutativity to rewrite it as 2 to the n plus 1 all over 2 to the n times n factorial all over n plus 1 factorial. Then we're going to use the recursive definition for factorials. So n plus 1 factorial is the same as n plus 1 times n factorial. Okay, I talked about that, I think, in the last video. So what we end up with then is the limit as n goes to infinity of the absolute value. So we have 2 to the n plus 1 over 2 to the n, which is just going to be 2 to the n plus 1 minus n, which is just 2, and then times n factorial all over n plus 1 times n factorial. Then that'll equal the limit as n goes to infinity of the absolute value of the n factorials cancel, and you're just going to have 2 all over n plus 1. Okay. The absolute values aren't necessary because as n goes to infinity, all these 2 over 10 plus 1, 2 over 100 plus 1, all of those are going to be positive. So the absolute value for this question doesn't really matter. It does later on, but not right now. So anyways, this is going to end up being L over infinity, which of course will just go to 0. And going back to your criteria then, if your R value, which is what this thing is, this is the R value that we talk about in our criteria here. If R is less than 1, the series is absolutely convergent. So hence, the series is absolutely convergent. Okay, so that's your video quiz for homework set 7. That's the second problem in the set. Okay, let's look at another one. Let's use the root test this time. So usually you'll use the root test when you have, well, use the ratio test, I mean most of the time, like 90% of the time. The root test kind of often is a shortcut, and it gives you a way of getting rid of that n exponent. So it's 7/8 to the n. You could use the root test to get rid of that because the root test involves an nth root, right? So let's look at it. The R equals the limit as n goes to infinity of the nth root of n times 7/8 to the n. Okay? And the nth root of a product is equal to the product of the nth roots, so you can rewrite this as the nth root of n times 7/8 to the n, and then you're taking the nth root of that. Okay. So this thing right here, this second factor, you could rewrite as 7/8 to the n to the 1 over n. And then you see, well, I can use my rules of exponents. So you've got a to the x to the y. It's just a to the x times y. You just multiply the exponents. So n times 1 over n is just 1. And that will be then just 7/8. Right? So this will just be 7/8. In other words, you're looking then at the limit as n goes to infinity of 7/8 times the nth root of n. It may not be clear what the nth root of n goes to, but if you play with your calculator a lot, sometimes you note things. And the nth root of n is actually going to go to 1. Okay, so to prove that to you, just here below, maybe write it in a different color or something, this fact, limit of the nth root of n as n goes to infinity. You can rewrite this as the limit of n to the 1 over n, and then use your calc 1, or sorry, your L'Hopital's rule, so that's like a calc 2 thing. You get e to the ln of n to the 1 over n, and then you could use the power rule to bring that in front. So you get the limit of e to the 1 over n times ln of n, which is, then you could pass the limit inside the exponential, so e to the limit as n goes to infinity of ln of n all over n. That thing there is infinity over infinity form, so you can do L'Hopital's on it, and you end up with the limit as n goes to infinity of 1 over n, which of course the limit of that thing, that's an L over infinity, so that's just 0, so you get e to the 0, which is 1. Okay, so yeah, that limit is going to end up being the R value. R will end up equaling 7/8. And then you just go to the criteria for your R value. If R is less than 1, which it is in this case, the series is absolutely convergent. And so hence, by the root test, the series is absolutely convergent. Okay, let's look at one that doesn't work out. So the series from n equals 1 to infinity of -1 to the n plus 1 times n plus 2 all over n plus 1 times n. Okay, looks like a nightmare, right? Okay, I'm going to use the ratio test. So I have the limit as n goes to infinity. And whenever you have these absolute values and you're plopping in a -1 to the n, or -1 to the, whatever, the absolute values will cancel those out. So you need not even write them. Okay, so I'm not going to have to write -1 to the n plus 1 plus 1. In other words, -1 to the 2n plus 1. No, just omit them completely. So the only thing I'm going to include is the n plus, from the numerator is the n plus 2. And of course, I'm looking at a sub n plus 1. So this will be n plus 1 plus 2, which will be n plus 3. And the denominator I have n plus 1 times n plus 1 plus 1, which is n plus 2. And then divided by, in other words, multiplied by the reciprocal of the original expression. So I have n times n plus 1 all over n plus 2. Okay. You can, if you want to, you can literally just sit there and FOIL that thing out. But ultimately, at the end of the day, when you do FOIL it and multiply it out, the big term is going to be n cubed, right? And then from the denominator, the leading term will be also n cubed. So you're going to end up with just the limit of 1, which of course is 1, which is inconclusive. So hence, the test is inconclusive. So the remedy is to use the nth term test. So if you do get an inconclusive, you got to turn around and use a different test in order to make your conclusion. So note the limit of the terms of the series limit of -1 to the n plus 1 all over n plus 2 all over n times n plus 1. Well, wait a second. This thing is going to equal 0. The limit of that is actually 0. So I'm not going to be using the nth term test. I'm not going to be able to do that. I'm going to have to do the alternating series test, and I think that will do the job. Sorry about that. So it's inconclusive. So instead, let's note the nth term test. Or sorry, the alternating series test. So we will use the alternating series test and note the following two things then. So first, the limit of the a sub n portion of the terms of the series. The limit of that thing. So it's n plus 2 all over n times n plus 1 as n goes to infinity. So if you were to distribute the bottom n, you're going to end up with n plus 2 all over n squared plus n. And then we could do that trick, and you just end up with 1 over n as n goes to infinity of 1 over n. And then that'll equal 0. Okay, so the first criteria is met. Second criteria, I need to show that it's decreasing. So a sub n plus 1 will be n plus 3 all over n plus, and I kind of already done that math above, right? So n plus 1 times n plus 2. I didn't do it in its completion though, so I'm going to have to kind of multiply it out and figure out what we got. But this thing then is equal to n times n squared plus 4n plus 3 all over n plus 1 times n squared plus 4n plus 4. At this point, you can see it's going to be true because you'll have two integers multiplied together, two positive integers in the numerator, where each integer is less than the integers in the denominator. So you can see, in the numerator, n is going to be less than n plus 1. And then n squared plus 4n plus 3 will definitely be less than n squared plus 4n plus 4. So let's just cut it at that point and say, well, that's definitely less than 1 for n greater than or equal to 1. Okay? So hence the thing is actually convergent. The series converges. Okay. Okay, so you're not out of the woods even if you get this one conclusion, this r equals 1. That just means you got to back up and try something else. Okay, it's a real bummer. So anyways, let's look at maybe two more, and then we'll talk about the proof. I'll give you a general kind of method for doing tests, these convergence tests, and then I'll talk about the proof of the. So at the end, if you don't want to watch the proof, I know some of these proofs are long, you could just sort of stop the video. Okay, so anyways, in future I'll try to do that, but I don't always. I don't have my kind of notes written out in that way. So anyways, another example, right? So I have the series n equals 1 to infinity of n factorial all over n to the nth power. So again, I'm going to pull the ratio test. Okay, so I'll have a sub n plus 1 is n plus 1 factorial all over n plus 1 raised to the n plus first power. Times n to the nth power all over n factorial. Okay. I'm going to realign things using the commutative property and properties of fractions. So I can rewrite this as n plus 1. And not only that, I'm going to rewrite n plus 1 factorial as n plus 1 times n factorial using that recursive definition all over n factorial. Another way you can handle factorials, if you have something like n factorial all over n plus 1 factorial, just to the side here, you can totally expand them and then cancel, which is the way I used to do it back in the day. So you'd go n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And below that you have n plus 1 times n plus 1 minus 1, which is n, times n minus 1 times n minus 2, dot, dot, dot. And it always ends in 3 times 2 times 1. So here you see sort of the cancellation happening. It's the n factorial with the n factorial leaving you with 1 over n plus 1. Okay. In this example here, we just have the reciprocal of that, so it should just be n plus 1 at the end of the day. And you can kind of see already, yeah, these will cancel, and you just have n plus 1. Okay, so anyways, this is times n to the n all over n plus 1 to the n plus 1. And I'm going to rewrite that too. So that's n plus 1 to the n plus 1 is the same as n plus 1 to the n times n plus 1 to the 1. Okay. So why did I do that? There's another cancellation there then, right? So I could cancel this guy with this guy, and then maybe have an easier limit to evaluate, right? So looks like I'm getting n to the n all over n plus 1 to the n. Then you could rewrite that as just something raised to the nth. So it'd be 1 to the infinity power type. Okay. So the limit as n goes to infinity of n all over n plus 1. So another rule of exponents we're taking advantage of to rewrite it. Okay. Okay, so once we get it in this form, we could take the limit as n goes to infinity of e to the n ln of n plus 1, n over n plus 1. Then we can move the limit inside the exponential, and then we can drop the absolute value signs. We don't need those anymore. And we'll have the limit as n goes to infinity of n times the ln of n over n plus 1, which is infinity times 0 form. Okay. As n goes to infinity, n will go to infinity. As n goes to infinity, n over n plus 1 will go to 1, and then the ln of 1 is 0. Okay. So we want to rewrite that. We'll get e to the limit as n goes to infinity of the ln of n all over n plus 1 all over 1 over n. Okay. And now we have a 0 over 0 form. So we can go ahead and do L'Hopital's, get e to the limit, so n goes to infinity of, to make the numerator a little easier to work with, you can rewrite it as ln of n minus ln of n plus 1, and then take its derivative. So the derivative in the numerator would end up being 1 over n minus 1 over n plus 1, and then all over the derivative of 1 over n is going to be negative 1 over n squared. Okay. I guess I don't need the absolute values there, but let's just put parentheses there. Let's get carried away. Okay, so now it's e to the limit of that thing, and we're going to algebraically simplify it first, right? So find a common denominator in the numerator, and the first term I need to multiply top and bottom by n plus 1, and the second term I need to multiply top and bottom by n. So I'm going to end up with n plus 1 all over n times n plus 1. Combining numerators, so minus then n, and then that's all over negative 1 over n squared. Okay. This will be then e to the limit of n plus 1 minus n is just 1, all over n times n plus 1, times the reciprocal of 1 over n squared, which is n squared over 1. And then we have e to the limit of negative n squared all over n squared plus n, okay, as n goes to infinity. So then we could play the trick where you're circling the high degree terms. So negative n squared over n squared is just negative 1. So we end up with e to the negative 1, which is 1 over e, which is definitely less than 1, because e is like 2 point something. Okay. So hence it's absolutely convergent. Okay. Let's look at one of these funky ones where you have the weird kind of odd factorial. So we have the series from n equals 0 to infinity of negative 1 to the n plus 1 times n factorial all over 1 times 3 times 5 dot 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 all the way up to 2n plus 1. Then we're taking limits. We're going to do the ratio test. Okay, so it's a limit as n goes to infinity of the absolute value. The absolute value will get rid of that negative 1 to the n plus 1 business. So we're just left with n plus 1 factorial all over 1 times 3 times 5 dot 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 all the way up to 2n plus 1, and then the last one will be replace n with n plus 1. You get 2n. It'll be 2 times n plus 1 plus 1, which will be 2n plus 2 plus 1, which will be 2n plus 3. Okay. And then multiply by the reciprocal of the original expression, so that would be 1 times 3 times 5, dot, 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 all the way up to 2n plus 1, all over n factorial. Okay. And then we can do some simplification. So I got n plus 1 factorial is the same as n plus 1 times n factorial. The other guy, there's a huge cancellation, right? There's just all of this junk is all of this junk. So you're just left, in the denominator, you're just left with 2n plus 3 times n factorial. The n factorials cancel, and you're left with the limit as n goes to infinity of the absolute value of n plus 1 all over 2n plus 3. And then you could play the trick where you're just circling terms. So you get n over 2n, and then that will just be 1/2, okay, which of course is less than 1, which implies it's absolutely convergent. Hence, the series is absolutely convergent. Okay, just one more note on factorials and how they cancel. Let's say you had something like your a sub n was 1 all over 2n factorial. But let's try to cancel that thing. And maybe that's an issue, maybe not. Let's just look at it. So a sub n plus 1 all over a sub n would equal 1 all over 2 times n plus 1 factorial all over 1 all over 2n factorial. Okay? This would be 1 all over 2n plus 2 factorial times the reciprocal of the denominator, which is 2n factorial over 1. Okay. So what is that then? Well, if you were to literally expand the factorial, going all the way down instead of just using the recursive definition, which, I mean, you can use the recursive definition. That's not going to, it'll be easier with that, but let's expand it all the way down. So the first term is 2n. The second term will be 2n minus 1. Okay. The third term will be 2n minus 2. And then you go all the way down to 3 times 2 times 1. Okay. In the denominator, we have 2n plus 2 times 2n plus 2 minus 1, which is plus 1, times 2n plus 2 minus 2, which is just 2n. And then you see the cancellation that's going to happen there. And then you have 1 less than that, and all the way down to 3 times 2 times 1. So that stuff cancels, and you're just left with 1 all over 2n plus 2 times 2n plus 1. And of course, if that was your series, and you took the limit of this thing all the way through, you would get 0, and it would be absolutely convergent. Okay. Okay. So anyways, we've gone through all the tests we basically have. What I want to give to you here is just a general strategy for testing and you may even want to try to build a flow chart to help you out. That might help. But like in the book Calculus for Dummies, I think they have like a flow chart in there for this kind of stuff. But this is the way it works. You always kind of start with the nth term test. Okay, because if the limit of the terms of the series do not equal 0, then it's divergent and you're done. Okay. Then you kind of move on to the series that you can identify. Like you ask yourself, is the series geometric? Is the series telescoping? Is the series a p-series? Is the thing an alternating series? Because you can see that, you can see there's definitely a difference between a geometric and an alternating series, and just by looking at it, you can kind of figure out which one it is, because especially for alternating series, it has that -1 thing. So hopefully it's kind of all right. Once you look at those and you say, okay, maybe it's not going to work, then you try the ratio test or the root test. And if those guys aren't working, go to the higher powered kind of tests. So the integral test is pretty straightforward, but it does take time. Then the comparison test you kind of leave for last. So can I do one of the comparison tests? So direct or limit comparison. Those are usually a little more, they're a little harder, because you have to call upon your brain to sort of do some work there. But the other ones are kind of just, I can get a computer to figure those out. But for this one, maybe a little bit of creative work on your part that can't be programmed into a computer. So that's the idea. Leave it at that. And then I'm going to do the proof for the ratio test right now. And so you don't need to watch this last part if you don't want to. I'm just doing it for completion. Okay. So I'm going to do the proof of the ratio test. Right. So we're going to suppose, we'll prove if r is less than 1, it's convergent. So I'm going to suppose that the limit of the absolute value of a sub n plus 1 all over a sub n is equal to some r value which is less than 1. Okay. Then I'm going to choose some value in between r and 1 and call it big R. So choose a big R such that r is in between. So first off, r, the limit of this thing is going to be greater than 0. Okay, so we could say 0, r is greater than or equal to 0 rather, because we're taking the limit of positive things. There's no way that it's going to be less than 0. And then we can wedge this big R value in between R and 1. Okay, that's just a fundamental property of the real numbers. Between any two numbers, you can find another number. Okay. Okay. Then we're going to invoke the strict definition of a limit. So by the strict definition of the limit, there exists some big N value such that if the terms of our sequence, if the n values, so a sub 1, a sub 2, a sub 3, if a sub n, if that n value is greater than big N, such that if n is bigger than big N, then the a sub n, the ratio of a sub n plus 1 all over a sub n will be less than big R. Okay, so what does that mean visually? And what you think of is this thing as kind of a sequence unto itself, right? So R1, let's not use R, let's use T1 is equal to a sub 1, or a sub 2 all over a sub 1. T2, the second term, is a sub 3 all over a sub 2, etc. Okay, so what we're saying is that the sequence of terms actually converges to little r, okay, and then there's 1 up here, and then there's big R right here. Okay, and we're saying because of the strict definition, because this limit is equal to this number r, we can find an epsilon such that for the little n values greater than big N, so maybe the terms of our sequence were like this. But once we get past big N, all the terms of the sequence are kind of around here, so they're always going to be less than the R value, which is up here. Okay, it's just because of the strict definition you could do that. Okay, so what happens then? Well, now we can produce a string of inequalities. And what's going to happen then is we're going to kind of do a comparison test. Okay, so from this statement, we can multiply both sides by a sub n, and and we're going to start with big N. Okay, so we'll let n equal big N, I guess. Okay, so note then, because all n that are bigger than big N will fulfill this inequality, we could say that a sub big N plus 1 all over a sub big N is less than R, and then we can multiply both sides by the absolute value of a sub big N, and we get this inequality. So a sub big N plus 1 absolute value will be less than R times a sub big N. Okay. So from that point, we can basically say that for any n value longer in the sequence, right? So right now I'm like at a sub big N, where n is bigger than little n, and then the next term is a sub n plus 1, and then the next term is a sub n plus 2, and the next term is a sub n plus 3. And basically, the ratio of any of these two terms will equal these t values in the sequence, and the t values will be within that epsilon distance around R. In other words, they'll be less than R. So you can basically say also then a sub n plus whatever. You know, you could say a sub n plus 2 all over a sub n plus 1 is less than R. And then again, you can multiply by a sub n plus 1 on both sides, and you get a sub n plus 2 less than R times the absolute value of a sub n plus 1. Okay. Then you could borrow this guy and multiply both sides by R, r is greater than 0, so it's not going to affect the inequality. So I can multiply that by r, and I get r times the absolute value of a sub n plus 1 is less than r squared times the absolute value of a sub n. And then you could put these two statements together, okay, using the I guess, what was that, the transitive property of inequalities, and you can conclude then the absolute value of a sub n plus 2 will be less than big R times the absolute value of a sub n plus 1, which is less than r squared times the absolute value of a sub big N. Okay? So at the end of the day, what we're producing is kind of this this chain of inequalities where in general, we will be able to make a comparison between a sub n plus some other variable, let's just call it little n. We're going to be able to say that that thing is less than r to the little n times the absolute value of a sub n. Okay. So why is that important? Because now we're going to do a direct comparison. So consider then the series formed from this side. Okay? So we have, let me rewrite it as the absolute value of a sub n times big R to the n, from n equals 1 to infinity, okay? Or even 0 to infinity. Right? What is this thing? Well, it's just a constant. This a sub big N is just some constant times big R to the n. And what is that? That's a geometric series. Not only that, it's convergent because big R is assumed to be less than 1. Okay, so big R is less than 1 from this original inequality. So considering the series, we note it's geometric. And convergent. Okay. So from there, then we are comparing it. We're doing a direct comparison with this other series where the terms are from the left side of the inequality back here. Okay, so we can directly compare it with this other series, n equals 0 to infinity of the absolute value of a sub big N plus little n. And that implies, because of the inequality and the convergence of the kind of quote-unquote bigger series, that the littler, this series that I'm giving you now is convergent. So we know it is geometric and convergent. We directly compare it with this series, and we conclude this is also convergent, which this thing right here is also convergent. Okay. So what is that thing that I have? Well, that thing that I have is basically just a shortened version of the series absolute value of a sub n, which is the series that sort of the series that I care about, right? So this ratio test here is trying to figure out whether the series of a sub n converges, right? That's what this limit comparison does. And what we've kind of shown is that sort of a shortened version of that with the absolute values does converge. And if you remember back in the previous videos, I did mention that if the sum from n equals 0 to infinity of a sub n converges, then the sum from n equals like 50 to infinity of a sub n will converge. Okay? And that's kind of what this thing, like big N is like, maybe big N is 20. So what you're looking at is a series starting n equals 0 to infinity of a sub 20 plus n. So that's a sub 21 plus a sub 20, whoops, it's a sub 20 plus a sub 21 plus a sub 22, etc. Right? So this thing is a shortened version of kind of this other thing. So okay, let's get back on track. We know So this thing is geometric and convergent because of the inequality and doing a direct comparison and the fact that that thing is convergent. This thing will converge. This thing is just a shortened version of it's convergent, and it's a shortened version. So let me write that. We conclude that this is also convergent. This is a shortened version of the series absolute value a sub little n from n equals 0 to infinity, right? So from our previous work, we know that this is also convergent. Okay, and then from our work in the series on the section on alternating series, we know that if the series of the absolute value of the terms is convergent, that means that the original series is absolutely convergent and therefore convergent. So hence, the series without the absolute values, just a sub n, is absolutely convergent, which I think is kind of what we wanted to show, right? I mean, you have to go to the point where saying that implies it's convergent. If you look back at the original kind of criteria that are resulting, that's yeah. So if it's r is less than 1, then it's absolutely convergent. So the overview is kind of we use the strict definition to build this sequence of inequalities, or this chain of inequalities, and then we were able to kind of say that the terms on the left and the terms on these right, they always have this relationship. So if you use the terms on the right, you can build a geometric series which is convergent, and that forces the series with the terms on the left to also be convergent. The series with the terms on the left is just the absolute value of the shortened sort of version of the absolute value of the original series. And then from what we know about absolute convergence, if that series is convergent, the series of the absolute value of the terms is convergent, then the original series is absolutely convergent. And that's the end of our proof. Okay, so yeah, that about does it, and we'll see. Thanks for watching. We'll see you next time.